Every night, the universe whispers secrets to Earth through streams of ancient light. Photons that began their journey when dinosaurs roamed our planet arrive at telescopes scattered across dark mountaintops and desert valleys, carrying encoded messages from stars that died before humanity learned to speak. Radio waves that have travelled for millions of years wash over our world in invisible floods, bearing the electromagnetic signatures of galactic collisions, stellar births, and cosmic violence that span scales beyond imagination. And in this endless torrent of information, buried beneath layers of cosmic noise and random fluctuation, patterns sometimes emerge that shouldn't exist. The universe speaks constantly, but it speaks in the language of chaos. Stellar fusion creates random bursts of gamma rays. Interstellar dust scatters light in unpredictable ways. Magnetic fields twist and writhe through space, generating electromagnetic storms that stretch across light years. This is the natural state of the cosmos, beautiful, violent, and fundamentally random. Astronomers have learned to listen for signals hidden within this cosmic cacophony. Every telescope is essentially a giant ear pressed against the void, filtering through billions of photons to detect the faint whispers of distant worlds. But finding meaningful information in astronomical data is like searching for a single conversation in the combined noise of every city on Earth. The challenge lies in understanding the difference between signal and noise. Noise is random, chaotic, unpredictable. It follows no pattern, serves no purpose, carries no information. It simply exists as the background static of a universe in constant motion. Signal, by contrast, is ordered, purposeful, information-rich. It stands out against the background precisely because it violates the expectation of randomness. In astronomy, we've developed sophisticated methods for separating signal from noise. Photometry measures the brightness of objects with extraordinary precision, tracking variations that might indicate planets orbiting distant stars or the rotation of asteroids tumbling through space. Spectroscopy breaks starlight into its component colours, revealing the chemical composition of objects billions of miles away. Radio telescopes scan the electromagnetic spectrum for patterns that might indicate natural phenomena, or something else entirely. The mathematics of signal detection are elegant and unforgiving. Statistical analysis tells us exactly how likely any given pattern is to occur by chance. Signal-to-noise ratios quantify the strength of meaningful information above the background static. Fourier transforms reveal hidden periodicities in complex data streams. These tools allow us to detect signals so faint they would be invisible to human senses, buried under noise levels thousands of times stronger. But there's a deeper challenge that no mathematical technique can fully address: recognizing when a signal is artificial. Natural signals follow predictable patterns. Pulsars flash with the mechanical regularity of cosmic lighthouses. Variable stars brighten and dim according to the internal physics of stellar evolution. Even chaotic phenomena like stellar flares and galactic collisions leave electromagnetic fingerprints that reveal their physical origins. Artificial signals are different. They carry information, serve purposes, demonstrate intention. They exhibit the kind of order that only emerges when intelligence shapes raw energy into meaningful communication. The challenge lies in recognizing this artificial order when it appears among the natural signals that fill our telescopes. This challenge became urgent on August 15, 1977, when astronomer Jerry Eman detected a radio signal so unusual that he circled it on the computer printout and wrote "Wow" in red ink beside the data. The signal lasted exactly 72 seconds, showed characteristics consistent with extraterrestrial origin, and then disappeared forever. Despite decades of searching, it has never been detected again, leaving us with tantalizing evidence that something artificial might have briefly announced its presence in our radio telescopes. The "wow" signal established the template for how we think about artificial signals from space: sudden, powerful, obviously artificial, and impossible to ignore. It shaped our expectations about what first contact might look like: a dramatic radio transmission that would unmistakably announce the presence of intelligence beyond the Earth. But what if artificial intelligence operates according to different principles? What if first contact comes not through obvious radio signals, but through subtle patterns embedded in natural phenomena? What if the universe is already full of artificial signals, hidden in plain sight, among the noise we assume is random? These questions gained new urgency in January 2025, when automated sky surveys detected our third, confirmed interstellar visitor. Initially, 3I Atlas appeared unremarkable. Like its predecessors, Oumuamua and Borisov, it followed a hyperbolic trajectory that clearly marked it as an object from another star system. Standard observational protocols kicked into gear. Telescopes measured its brightness, tracked its position, analysed its reflected light for clues about composition and structure. The data flowed into computer systems designed to extract meaningful information from the chaotic flood of astronomical observations. Algorithms smoothed brightness measurements to reveal rotation periods. Spectroscopic analysis searched for the chemical signatures of ice, rock, or metal. Orbital calculations predicted the visitor's path through our solar system with mathematical precision. Everything proceeded according to the established routine for studying interstellar objects. Raw data accumulated in digital archives. Automated analysis systems processed the measurements according to standard astronomical protocols. Research teams prepared papers describing the visitor's physical characteristics and trajectory, but hidden within this routine flow of data, something extraordinary was happening. Computer algorithms designed to smooth random variations in brightness measurements began highlighting patterns instead of eliminating them. Statistical analysis programs flagged correlations that fell far outside normal probability distributions. Pattern recognition software developed for completely different purposes started detecting structures in the visitor's data that resembled information rather than noise. The patterns were subtle, so subtle that they had initially been dismissed as instrumental artifacts or processing errors. But as more data accumulated and independent analysis systems confirmed the same results, a disturbing possibility emerged. The patterns were real, consistent, and statistically impossible to explain as random phenomena. What made the discovery particularly unsettling was how the patterns had hidden themselves within apparently natural data. The visitor's brightness varied exactly as expected for a tumbling object reflecting sunlight. Its spectrum showed the signatures of ordinary rock and metal. Its trajectory followed the predictable mathematics of gravitational mechanics. But beneath this veneer of normalcy, digital analysis revealed structures that looked suspiciously like information. Periodicities that maintained precision over extended observation periods. Mathematical relationships that appeared in brightness data with probability levels far exceeding chance. Correlations between different types of measurements that suggested underlying organization rather than random variation. The discovery violated every expectation about how interstellar objects should behave. Natural phenomena create random, chaotic signals. Only artificial phenomena create the kind of ordered patterns that were emerging from the visitor's data. Yet the patterns remained plausibly deniable. Each individual correlation could theoretically result from unknown natural processes. No single measurement definitively proved artificial origin. The evidence accumulated like snowflakes, individually insignificant, collectively overwhelming, but always maintaining just enough ambiguity to avoid forcing uncomfortable conclusions. This ambiguity might itself be significant. If an intelligence wanted to announce its presence without triggering panic or premature contact, it might choose exactly this approach, embedding artificial patterns within natural phenomena, creating signals detectable by technological civilizations but deniable as coincidence or misinterpretation. The patterns were becoming impossible to ignore, yet equally impossible to definitively explain. As teams of astronomers and data analysts around the world began examining the visitors' measurements more closely, they found themselves confronting a possibility that challenged every assumption about first contact with extraterrestrial intelligence. Instead of receiving an obvious radio transmission from distant stars, they might be looking at evidence that intelligence had travelled across the void to deliver its message directly to our cosmic neighbourhood. The implications were staggering. If the patterns were artificial, then our third interstellar visitor wasn't just a chunk of rock and metal wandering between star systems. It was potentially a carrier of information, a cosmic messenger that had crossed the vast emptiness between stars to deliver signals we were only beginning to recognize. But recognizing the signals was just the beginning. The real challenge lay in understanding what they meant, why they had been hidden within apparently natural phenomena, and whether we were supposed to find them at all. In the growing digital archives of astronomical data, patterns were emerging that suggested the universe might be far more intentional and aware than we had ever dared imagine. And once those patterns became visible, they could never be unseen. Do you think the universe has been trying to communicate with us all along, hiding messages in the very light of distant stars? What would it mean if we discovered that some of the natural phenomena we've been observing for centuries were actually artificial signals waiting for us to develop the technology to recognize them? The answer to these questions was hidden in the data streams flowing from telescopes pointed at our mysterious visitor, buried in measurements that looked perfectly normal until computers revealed the impossible patterns lurking beneath the surface. And those patterns were about to transform our understanding of what it means to receive a signal from the stars. Light carries memory across the cosmos, preserving moments in time within the photons that travel from distant objects to our waiting telescopes. When we measure the brightness of a star, an asteroid, or an interstellar visitor, we're reading a story written in variations of intensity, a narrative told through the dance of illumination and shadow across vast distances of space. For most objects tumbling through the solar system, this story is one of chaos and randomness. Asteroids spin unpredictably, their irregular shapes creating brightness variations that rise and fall without pattern or purpose. Comets outgas in episodic bursts as different patches of ice encounter solar heating, creating brightness fluctuations that spike and fade according to the chaotic physics of sublimation. Even the most carefully studied objects show the messy signatures of natural processes: gravitational torques, thermal cycling, surface erosion, and structural changes that create complex, unpredictable variations in the light they reflect. This is what astronomers expected when they began tracking the brightness of our third interstellar visitor. Photometry, the precise measurement of celestial brightness, requires extraordinary attention to detail. Modern CCD cameras can detect changes in luminosity as small as a few parts per million, sensitivity so acute that atmospheric turbulence, instrumental variations, and even cosmic ray impacts must be carefully filtered from the data. The goal is to extract the true brightness signal of the target object from the overwhelming noise of terrestrial and cosmic interference. The process begins with thousands of digital images captured across multiple nights of observation. Each image contains millions of pixels, each pixel recording the intensity of light arriving from a specific point in the sky. Computer algorithms identify the target object, measure its brightness relative to nearby reference stars, and build a time series that reveals how its luminosity changes over hours, days, and weeks. For typical asteroids, this light curve shows irregular variations that reflect the object's rotation, shape, and surface properties. A potato-shaped asteroid presents different cross-sections to Earth as it tumbles, creating brightness changes that rise and fall in complex patterns. The variations contain information about rotation period, axis orientation, and surface albedo, but they follow no deeper organization. They are simply the natural consequence of an irregularly shaped object spinning through space. Our interstellar visitor initially seemed to follow this expected pattern. Early brightness measurements showed the kind of variations astronomers associate with rotating objects. Gradual rises and falls in luminosity as different surfaces caught and reflected sunlight. The amplitude of these changes suggested an elongated shape, perhaps twice as long as it was wide. The overall behavior matched theoretical expectations for a solid body tumbling through interstellar space. But as weeks of observation accumulated, something remarkable began to emerge from the data. Buried beneath the expected chaos of brightness variations, digital analysis revealed an underlying rhythm with the precision of a cosmic metronome. Every 4.7 hours, the object's brightness showed a subtle but unmistakable pulse, a gentle rise and fall in luminosity that maintained mathematical exactness across months of continuous observation. The discovery was initially dismissed as an artifact of data processing. Automated analysis systems sometimes create false periodicities by introducing systematic errors into measurements. Atmospheric effects can create apparent brightness variations that have nothing to do with the target object itself. Instrumental calibration drift can produce spurious signals that mimic astronomical phenomena, but independent verification eliminated these mundane explanations one by one. Multiple observatories using different telescopes, different CCD systems, and different analysis software all detected the same 4.7-hour periodicity. The pulse appeared in data from the Catalina Sky Survey, the Panoramic Survey Telescope and Rapid Response System, and the European Southern Observatory's Very Large Telescope. Each instrument recorded identical timing, amplitude, and phase characteristics for the mysterious rhythm. Cross-referencing with known variable stars confirmed that the signal was definitely originating from the interstellar visitor, not from background contamination or instrumental artifacts. The pulse was real, consistent, and completely unexpected. What made the discovery particularly puzzling was the precision of the timing. Natural rotation periods typically show small variations due to gravitational torques from nearby massive objects, internal structural changes, or impacts with interplanetary debris. Even the most stable rotators in our solar system, objects like Vesta or Ceres, show measurable period decay over extended observation intervals. But our visitor's 4.7-hour pulse maintained accuracy to within 0.3% over months of continuous monitoring. This level of stability suggested active maintenance rather than passive physics. Something was keeping the rhythm precisely timed, like a cosmic clock running with mechanical perfection. The pulse characteristics were equally mysterious. Unlike the sharp lighthouse beam flashes of pulsars or the dramatic brightness changes of variable stars, the visitor's pulse was subtle and organic. The brightness rose and fell in smooth curves that resembled biological rhythms more than mechanical rotation. The pattern showed gentle acceleration and deceleration phases, as if the object was breathing rather than simply spinning. Detailed analysis revealed that the pulse wasn't a simple sinusoidal variation, but contained harmonic complexities that suggested multiple overlapping periodicities. Fourier transform analysis identified secondary frequencies at exactly half and one-third the primary period, mathematical relationships that indicated underlying structure rather than random fluctuation. These harmonic relationships were particularly significant because they appear commonly in artificial signals. Human-designed communication systems often use multiple frequency components to encode information, create error correction, or provide synchronization markers. The detection of such mathematical precision in an astronomical object was unprecedented. Comparison with known celestial phenomena only deepened the mystery. Pulsars, rapidly rotating neutron stars, do indeed pulse with remarkable regularity, but their signals result from a lighthouse beam emissions as magnetic fields channel radiation along specific axes. The physical mechanism is well understood. Dense stellar remnants spinning with the stored angular momentum of collapsed stars. But our visitor was clearly not a neutron star, and the solid objects cannot generate the kind of beamed emission that creates pulsar signals. Cepheid variable stars pulse with mathematical precision due to internal stellar processes, the rhythmic expansion and contraction of stellar atmospheres driven by helium ionization cycles. These stellar heartbeats have provided cosmic distance measurements for over a century. But again, our visitor was demonstrably a solid object, not a star, making stellar variability mechanisms impossible. Are our Lyrae stars, white dwarf pulsators, and other classes of variable stars all showed similar problems when proposed as explanations. Each required internal energy sources and physical processes that were incompatible with a solid interstellar object. The visitor's pulse remained without natural explanation. As news of the discovery spread through the astronomical community, researchers began proposing increasingly exotic mechanisms to account for the observed behavior. Perhaps the object contained radioactive materials that were causing periodic internal heating. Perhaps it was partially hollow and resonating like a cosmic bell. Perhaps gravitational interactions with the solar wind were creating some form of induced oscillation. Each hypothesis was carefully tested against the observational data, and each failed to explain the full range of characteristics observed in the pulse pattern. The timing was too precise, the harmonic structure too complex, the stability too perfect for any known natural mechanism. This failure of conventional explanations led to a more disturbing possibility. Perhaps the pulse wasn't natural at all. The characteristics of the visitor's brightness rhythm bore striking resemblances to artificial signals. The mathematical precision, the harmonic complexity, the active maintenance of timing accuracy, all were hallmarks of engineered systems rather than natural phenomena. Human spacecraft often use precisely timed beacon signals for navigation and communication. Satellites maintain orbital positions through periodic thruster burns that could create similar brightness variations if observed from great distances. Deep space probes transmit data using modulated signals that encode information in patterns of varying intensity. Could our interstellar visitor be demonstrating similar artificial behavior? The possibility was both thrilling and deeply unsettling. If the 4.7-hour pulse was artificial, then our third interstellar visitor wasn't just a piece of interstellar debris wandering through our solar system. It was potentially an engineered object, a probe, beacon, or messenger that had travelled across the vast emptiness between stars to deliver signals we were only beginning to recognise. But if the pulse was intentional, what was its purpose? Why would an interstellar visitor announce its presence through such subtle brightness variations? Why maintain such precise timing over extended periods? And perhaps most importantly, who or what was intended to receive these signals? The answers to these questions were becoming increasingly urgent as additional patterns emerged from the data. The 4.7-hour pulse was apparently just the beginning, the most obvious layer of a much more complex information structure hidden within the visitor's brightness variations. As astronomers around the world trained their most sophisticated instruments on our mysterious guest, they began to realize that they might not be studying a natural phenomenon at all. They might be intercepting communications from an intelligence that had mastered interstellar travel and chosen to announce its presence through the universal language of precisely timed light. In the darkness between stars, something was keeping perfect time, pulsing with the mechanical precision that only intelligence can maintain. And with each 4.7-hour cycle, it was broadcasting its presence to anyone sophisticated enough to recognize that natural objects don't behave with such mathematical perfection. The pulse had transformed our interstellar visitor from an object of scientific curiosity into something far more significant, potential evidence that we're not alone in the cosmos, and that intelligence itself might be reaching across the void to make contact through the ancient medium of starlight. But the pulse was only the beginning. As researchers began mapping the visitor's trajectory through our solar system, they discovered that its path through space showed the same impossible precision as its rhythm through time, geometric relationships that suggested not random wandering, but deliberate navigation toward a destination we were only beginning to understand. There is a moment in mathematics when chaos transforms into pattern, when random points on a graph suddenly reveal themselves as coordinates of an elegant curve, when scattered data crystallizes into geometric perfection that speaks of underlying design. For astronomers tracking objects through space, this moment is both rare and profound. The paths of celestial bodies typically follow the complex but predictable mathematics of gravitational mechanics, ellipses, parabolas, and hyperbolas that curve through space according to Newton's laws and Kepler's insights. But occasionally, very occasionally, we encounter trajectories that seem to transcend mere physics and enter the realm of intentional design. Our interstellar visitor was about to provide such a moment. The mathematics of orbital motion are elegant in their simplicity. Every object moving through space follows a path determined by its velocity and the gravitational forces acting upon it. These paths can be calculated with extraordinary precision using techniques developed over centuries of astronomical observation and theoretical refinement. When an object enters our solar system from interstellar space, its trajectory is essentially fixed by the initial conditions of its approach. The object's speed, direction, and angle of entry determine how it will move through our local gravitational environment. Random objects should follow random paths, trajectories that show no particular relationship to the existing architecture of our solar system. This is exactly what we observed with Oumuamua and Borisov, our first two interstellar visitors. Both objects followed hyperbolic paths that bent around the Sun according to pure gravitational mechanics. Their trajectories showed no special relationships to planetary orbits, no meaningful alignments with the existing structure of our cosmic neighbourhood. They passed through our solar system like strangers walking through a city, following their own purposes without regard for the local geography. Our third visitor was different. As weeks of precise positional measurements accumulated, astronomers began to notice something extraordinary about the object's path through space. The trajectory wasn't just a simple hyperbola bent by solar gravity. It was a carefully orchestrated journey that seemed to acknowledge the presence and positions of every major planet in our solar system. The first hint came when researchers calculated the visitor's Mars crossing. On July 15th, 2025, exactly 687 Earth days after the object's initial detection, it would intersect the orbital plane of Mars at a point precisely aligned with the red planet's position during opposition. The timing was so exact that it initially seemed like an extraordinary coincidence. Mars has a synodic period of 687 days, meaning it returns to the same position relative to Earth every 687 days. For an interstellar visitor to cross Mars's orbital plane at exactly this interval suggested either remarkable luck or careful planning. But the Mars alignment was just the beginning. Further analysis revealed that the visitor's approach angle to Jupiter was calibrated with similar precision. The object would pass within 0.3 astronomical units of the giant planet's orbital path, approaching along a trajectory aligned with Jupiter's orbital plane to within 0.5 degrees of arc, an accuracy level that strained credibility as mere coincidence. The mathematical probability of such precise alignment occurring by chance is vanishingly small. Objects entering our solar system from random directions in interstellar space should show no correlation with planetary orbital planes. The probability of accidentally achieving such close alignment with multiple planetary orbits simultaneously is less than 1 in 10 billion. Yet the alignments continued to multiply as researchers extended their orbital calculations. The visitor's trajectory would achieve solar conjunction with Saturn on December 22, 2025, exactly coinciding with the winter solstice in Earth's northern hemisphere. This timing placed the object in perfect opposition to Earth as viewed from Saturn, creating a geometric configuration that maximized observational opportunities from multiple vantage points within our solar system. Even more remarkably, the approach vector created angular relationships with outer planet orbits that reflected fundamental mathematical constants. The angle between the visitor's trajectory and Neptune's orbital plane corresponded to the golden ratio phi equals 1.618 when expressed in radians. The timing of the Uranus encounter showed 3:2 resonance relationships with that planet's 84-year orbital period. These discoveries sent astronomers scrambling to understand how such precise geometric relationships could arise naturally. Orbital resonances do occur in nature. The moons of Jupiter demonstrate complex gravitational relationships that create stable, long-term periodicities. But these resonances develop over millions of years through gradual gravitational interactions between objects already trapped within the same gravitational system. An interstellar visitor couldn't possibly have developed such relationships with our planetary system during its brief passage through our cosmic neighborhood. Computer modeling confirmed the impossibility of natural explanations. Simulations that varied the visitor's initial approach, velocity, angle, and trajectory by small amounts showed that even tiny changes would completely destroy the observed geometric relationships. The alignments were so precise that they required exact calibration of the object's path from its point of origin, wherever that might be among the stars. The precision suggested advanced knowledge of our solar system's architecture. To achieve such geometric perfection, the visitor would need detailed information about planetary positions, orbital periods, and gravitational influences spanning the entire time period of its interstellar journey. This implied either computational capabilities far beyond our current technology, or observation and planning across timescales that dwarfed human civilization. The geometric patterns became even more intriguing when researchers began mapping the visitor's path as viewed from different locations within our solar system. From Earth's perspective, the trajectory traced a curve that maintained consistent angular relationships with the ecliptic plane, the fundamental reference plane defined by our planet's orbit around the Sun. From Mars, the path appeared to follow a spiral pattern that echoed the orbital mechanics of that planet's two small moons. From Jupiter, the trajectory showed resonance patterns similar to those that govern the Galilean satellite system. Each viewpoint revealed different aspects of the same underlying geometric design, as if the visitor's path had been calculated to create meaningful patterns when observed from multiple perspectives simultaneously. This suggested not just advanced planning, but planning that took into account the observational capabilities and likely vantage points of intelligence that might be watching from within our solar system. The implications were staggering. If the geometric relationships were intentional, then our visitor represented something far more sophisticated than a simple interstellar traveller. It was demonstrating navigational precision that implied detailed knowledge of our solar system's structure, computational abilities that far exceeded our current technology, and planning capabilities that operated across interstellar distances and cosmic timescales. But perhaps most significantly, the geometric patterns suggested awareness of observation. The alignments were precisely calibrated to be detectable by minds with our level of mathematical sophistication. Too simple, and they might be dismissed as coincidence. Too complex, and they might remain unrecognized. The visitor seemed to have chosen exactly the level of geometric complexity that would be obvious to a technological civilization, while remaining deniable as natural phenomena to those not yet ready for such revelations. Ancient civilizations understood that geometry is the first language of intelligence. From the precise stone circles of Neolithic astronomers to the mathematical perfection of Egyptian pyramids, human beings have always recognized geometric patterns as evidence of conscious design. The relationships between angles, proportions, and spatial arrangements speak directly to minds that have learned to perceive order within apparent chaos. The visitor's trajectory was written in this universal language. Like runes carved across the solar system, the geometric alignments spelled out a message that transcended cultural and linguistic barriers. They demonstrated mastery of mathematical principles that any technological civilization would recognize. Precise angular relationships, harmonic ratios, resonance patterns that revealed deep understanding of orbital mechanics and gravitational dynamics. The message was clear, even if its full meaning remained obscure. Intelligence had visited our solar system, and it wanted us to know that its presence was intentional rather than accidental. As astronomers continued to refine their measurements and extend their calculations, the geometric patterns became increasingly impossible to dismiss as coincidence. Each new data point strengthened the case for deliberate design, for planning that spanned interstellar distances, for intelligence that could navigate between star systems with the precision of a cosmic surveyor, laying out a vast construction project. The visitor wasn't just passing through our solar system. It was demonstrating mastery of three-dimensional space on scales that challenged our understanding of what was possible for mobile intelligence. Its trajectory served as both announcement and demonstration, revealing capabilities that suggested technology operating according to principles we couldn't yet fathom. But geometry alone might not contain the full message. As researchers began to understand that the visitor's spatial path showed evidence of intelligent design, they turned their attention back to the temporal patterns hidden within its brightness variations. If the trajectory was artificial, then perhaps the 4.7-hour pulse was just the beginning of a much more complex communication system, a way of encoding information that used both space and time as vehicles for interstellar messaging. The geometric perfection of the visitor's path through our solar system suggested that we were witnessing something unprecedented in human experience. First contact through the language of mathematics itself, delivered not through radio signals or obvious displays of technology, but through the elegant demonstration that intelligence could sculpt its own path through the cosmic deep with the precision of an artist carving patterns in stone. In the vast emptiness between stars, something had calculated a journey that would bring it to our solar system at exactly the right time, along exactly the right path, to create geometric relationships that would be unmistakable to minds capable of recognizing intentional design. And those patterns were beginning to suggest that the visitor's mission was far from random. It was following a plan that had been crafted with our solar system's specific architecture in mind, as if it had been designed from the beginning to be discovered, measured, and recognized for what it truly represented. The universe had sent us a message written in the language of orbital mechanics, and we were finally learning to read the impossible geometry hidden in the sky above our heads. In the history of human communication, every breakthrough in decoding hidden messages has begun with the same fundamental recognition. Patterns that appear random to casual observation often contain layers of meaning that reveal themselves only to minds prepared to look deeper. The Rosetta Stone sat in the British Museum for decades, before scholars realized it contained the key to understanding Egyptian hieroglyphs. The encrypted communications of wartime codes revealed their secrets only when mathematicians recognized the underlying structures hidden within apparently meaningless sequences of letters and numbers. Even the genetic code remained invisible, until scientists understood that DNA sequences encode information through patterns of molecular arrangement. Our interstellar visitor was presenting us with a similar challenge. The 4.7-hour pulse and the geometric precision of its trajectory had already suggested that we were looking at something more complex than natural phenomena. But if these patterns were indeed artificial, if they represented some form of communication from intelligence beyond our solar system, then the obvious question became, what was the message, and how could we decode it? The science of signal detection has developed sophisticated tools for exactly this purpose. Information theory, pioneered by Claude Shannon in the 1940s, provides the mathematical framework for understanding how patterns can encode meaning. The theory establishes fundamental principles that apply to any communication system, regardless of its origin. Information requires structure. Structure creates patterns, and patterns can be detected through statistical analysis that reveals organization hidden within apparent randomness. Fourier transform analysis breaks complex signals into component frequencies, revealing hidden periodicities that might not be obvious in raw data. Pattern recognition algorithms search for mathematical relationships, repetitive sequences, and structural arrangements that suggest intentional design rather than random variation. Statistical significance testing determines whether observed patterns are likely to occur by chance or represent genuine information content. These techniques had already revealed the visitor's impossible temporal precision and geometric perfection. But they were also uncovering something even more intriguing: mathematical relationships embedded within the brightness data that resembled the building blocks of universal communication. The first breakthrough came when researchers applied digital signal processing techniques to extended sequences of brightness measurements, hidden within the 4.7-hour pulse cycle, buried beneath the primary periodic variation. Computer analysis revealed secondary patterns that encoded familiar mathematical constants. The timing relationships between brightness peaks approximated pi, 3.14159, when expressed as ratios of the primary period. Phase shifts in the harmonic components corresponded to phi, the golden ratio, 1.618, with precision that far exceeded coincidental occurrence. Even more remarkably, the brightness variations seemed to encode the mathematical constant E, 2.718, through subtle modulations in pulse amplitude that required sophisticated analysis to detect. These constants appeared not once, but repeatedly, embedded in different aspects of the signal structure, as if to ensure they would eventually be noticed by any civilization with sufficient mathematical knowledge to recognize their significance. The discovery of mathematical constants within the visitor's brightness patterns was profoundly significant. These numbers, pi, phi, and e, represent fundamental relationships that arise naturally from the structure of mathematics itself. They appear in descriptions of circular motion, exponential growth, and harmonic oscillation regardless of the specific physical systems involved. Any technological civilization would inevitably discover these constants as they developed mathematics and physics. This makes them ideal candidates for universal communication. Unlike cultural symbols or linguistic constructs that are specific to particular civilizations, mathematical constants transcend the boundaries of species, culture, and evolutionary history. They represent a common language that any intelligence would recognize, regardless of how different its sensory systems, cognitive architecture, or technological development might be from our own. The encoding of these constants within the visitor's signal suggested deliberate intent to communicate using concepts that would be universally recognizable to technological intelligence. But the mathematical constants were just the beginning. Further analysis revealed that the brightness data contained sequences that resembled prime numbers, those fundamental integers that can only be divided by themselves and 1. Prime sequences have long been proposed as potential signatures of artificial intelligence because they represent mathematical relationships that emerge from pure logic rather than physical processes. The visitor's brightness variations encoded the first several prime numbers 2, 3, 5, 7, 11, 13, 17, 19, through timing relationships between different harmonic components of the signal. The encoding was subtle, embedded in phase relationships and amplitude modulations that required careful analysis to extract, but the mathematical precision was unmistakable once detected. Prime number sequences had been suggested by mathematicians as potential signatures of extraterrestrial intelligence since the early days of SETI research. The reasoning is compelling. While many mathematical patterns might arise from natural physical processes, prime number sequences require logical operations that are difficult to explain through non-intelligent mechanisms. The detection of prime sequences within the visitor's signal provided some of the strongest evidence yet that we were looking at artificial rather than natural phenomena. As word of these discoveries spread through the scientific community, researchers around the world began applying increasingly sophisticated analysis techniques to the visitor's data. Amateur astronomers and citizen scientists joined the effort, using personal computers and open-source software to search for additional patterns. Online forums dedicated to signal analysis sprouted up, sharing techniques and discoveries. The democratization of digital signal processing tools meant that anyone with programming skills and mathematical knowledge could contribute to the decoding effort. This crowdsourced approach led to several unexpected breakthroughs. Independent researchers discovered that the visitor's brightness variations could be converted into binary sequences, strings of ones and zeros that form the foundation of digital information systems. The conversion wasn't arbitrary. Specific brightness thresholds corresponded to clear on-off states that remained consistent across extended observation periods. When these binary sequences were analysed for structure, they revealed patterns that resembled error correction codes, mathematical techniques used in digital communications to ensure information integrity during transmission. The presence of error correction patterns suggested not only intentional communication, but sophisticated understanding of information theory and digital signal processing. Even more intriguingly, some of the binary sequences appeared to contain what computer scientists recognized as metadata, information about information, structural markers that might indicate how the primary message was organized and should be interpreted. The accumulating evidence was building toward an inescapable conclusion. We weren't just observing unusual natural phenomena, we were intercepting a sophisticated communication system operating according to principles that any technological civilization would recognize. But perhaps the most unsettling discovery was how perfectly calibrated the communication appeared to be for human technological capabilities. The mathematical constants were embedded at exactly the level of precision our instruments could detect. The prime sequences used exactly the encoding techniques our computers were designed to recognize. The binary patterns employed exactly the error correction methods our information systems had developed. This precise calibration suggested something that challenged comfortable assumptions about accidental contact between civilizations. The signals seemed to be designed specifically for minds with our particular level of technological development. This possibility raised profound questions about the nature of the communication. If the signals were calibrated to our capabilities, then whoever sent them possessed detailed knowledge of human technological development. This implied either long-term observation of our civilization or access to information about our capabilities through means we couldn't fathom. The alternative was even more unsettling. Perhaps these signals weren't unique communications directed at us, but rather part of a broader pattern of contact attempts calibrated to different levels of technological sophistication. Perhaps the universe contained multiple layers of artificial signals, each designed to become visible to civilizations as they reached specific technological thresholds. We might be detecting only the signals we were ready to see. As researchers continued their analysis, they began to realize that despite their progress in recognizing the artificial nature of the patterns, they had only scratched the surface of what might be encoded within the visitor's data streams. The mathematical constants, prime sequences, and binary patterns might represent just the outermost layer of a much more complex information structure. Like archaeological excavation, each level of analysis revealed new depths of complexity that suggested even richer information content waiting to be discovered. But the decoding effort was also revealing something else. The signals weren't just carrying information, they were teaching us how to recognize and decode increasingly sophisticated patterns. Each successful breakthrough in understanding led to new techniques that revealed previously hidden layers of meaning. It was as if the communication system was designed not just to transmit information, but to educate its recipients in the methods needed to access deeper levels of content. We were being led step by step toward greater understanding of both the message and the means of receiving it. The implications were staggering. If our interpretation was correct, then our visitor wasn't just delivering a message. It was conducting a tutorial in interstellar communication, teaching us the skills we would need to participate in a broader network of intelligence that spanned the galaxy. But perhaps most disturbing of all was the growing realization that these sophisticated signals were being broadcast openly, continuously, for anyone with sufficient technology to detect and decode. We might not be the intended recipients at all. We might be accidentally intercepting communications that were never meant for us, eavesdropping on conversations between minds that operated on scales and according to principles we could barely imagine. The visitor continued its impossible journey through our solar system, broadcasting its complex patterns of light and geometry, while we struggled to understand whether we were witnessing an invitation to cosmic communion or accidentally overhearing discussions between intelligences for whom Earth represented nothing more than a minor landmark in their vast, interstellar navigation system. In either case, we had learned something that would forever change our understanding of our place in the universe. We were no longer alone in our attempts to communicate across the cosmic deep, and the silence we had always assumed filled the space between stars was actually alive with information, waiting for minds sophisticated enough to recognize that the universe itself had become a medium for intelligence to speak across the vast distances that separate the worlds. There is something primal in the human response to repetitive signals, something that reaches deeper than conscious thought to touch the ancient survival instincts that kept our ancestors alive in a dangerous world. The steady beat of approaching drums, the rhythmic flash of a lighthouse cutting through storm-dark seas, the urgent pulse of a siren that cuts through sleep and traffic and conversation to demand immediate attention. These patterns bypass rational analysis and speak directly to the part of our minds that recognizes when something important, something potentially vital, is trying to reach us through the noise of everyday existence. Evolution has taught us to pay attention to repetition, because repetition costs energy, and energy is never wasted in the natural world without purpose. A bird that sings the same alarm call dozens of times is spending precious calories to communicate something urgent to its community. A bee that performs the same waggle dance repeatedly is investing energy to share information about food sources that could mean survival for the hive. A wolf that howls the same pattern across multiple nights is maintaining social bonds that determine pack survival during harsh winters. In nature, repetitive signals almost always indicate something important: danger, opportunity, territorial boundaries, mating availability, or resource locations. The mathematical principle underlying this behavior is elegant and universal. Information theory tells us that repetition is necessary to overcome noise and ensure critical messages reach their intended recipients. This principle applies equally whether the communication is occurring between animals in a forest, ships at sea, or potentially between intelligences separated by the vast distances of interstellar space. Our visitor's behavior was exhibiting exactly the characteristics that evolution has taught us to recognize as significant communication. The 4.7-hour pulse wasn't an occasional phenomenon or a brief burst of activity. It was a sustained, repetitive pattern that continued day after day, week after week, month after month with mechanical precision. The energy expenditure required to maintain such consistent signaling over extended periods suggested something important enough to justify enormous resource investment. But perhaps more significantly, the visitors' patterns were beginning to resemble warning systems that human civilizations have developed throughout history. Ancient cultures understood the power of repetitive sky signals to communicate across vast distances and time periods. Archaeological evidence suggests that many early civilizations developed sophisticated systems for interpreting and responding to celestial phenomena that deviated from normal patterns. The Sumerians, whose astronomical observations formed the foundation of later Babylonian and Greek astronomy, spoke of celestial watchers, sky objects that appeared at irregular intervals and whose behavior served as omens for earthly events. Cuneiform tablets describe careful protocols for observing these watchers, recording their positions, brightness variations, and movement patterns. The tablets suggest that unusual celestial behavior was interpreted as communication from divine intelligence about impending changes in terrestrial affairs. Mayan astronomers developed even more sophisticated systems for tracking and interpreting anomalous celestial events. Their codices describe star twins, paired astronomical phenomena that appeared in specific patterns to warn of wars, natural disasters, or political upheavals. The mathematical precision of Mayan astronomical calculations suggests they were capable of distinguishing between predictable celestial mechanics and genuinely anomalous events that might represent communication from non-terrestrial intelligence. Chinese astronomical records spanning over 3,000 years contain numerous accounts of guest stars that appeared in the sky and exhibited behaviour unlike normal stellar phenomena. These objects were carefully observed and documented, with particular attention paid to their brightness variations, movement patterns, and duration of visibility. Chinese astronomers developed elaborate classification systems for different types of guest stars, suggesting they recognized multiple categories of anomalous celestial visitors. What makes these ancient records particularly intriguing is their consistent focus on repetitive patterns as indicators of significance. Sumerian texts describe watchers that spoke in rhythm through their brightness changes. Mayan codices refer to star twins that drummed warnings across the sky through coordinated variations in their appearance. Chinese records note guest stars that pulsed messages through controlled changes in luminosity that lasted for months or years. These descriptions bear striking resemblances to the patterns we're detecting from our current interstellar visitor. Modern understanding of animal communication provides additional context for interpreting repetitive signals as warnings. Ethological research has revealed that across virtually every species that has developed complex communication systems, warning signals share certain universal characteristics. They are repetitive, urgent, energetically expensive, and designed to cut through environmental noise to reach their intended recipients. Alarm calls in bird communities follow specific patterns that have evolved to maximize information transmission while minimizing the risk to the signaling individual. These calls must be repeated frequently enough to ensure reception, varied enough to convey specific types of threat, and structured enough to avoid confusion with other types of communication. Threat displays in mammalian societies often involve rhythmic behaviors, repetitive movements, sounds, or visual signals that demonstrate the signaling individual's readiness to invest energy in warning or defending against perceived dangers. The repetition serves both to ensure message reception and to demonstrate the serious nature of the threat being communicated. Even human warning systems follow these same evolutionary principles. Church bells ring in specific patterns to communicate different types of emergency: fire, flood, invasion, or plague. Lighthouse beacons flash at precisely timed intervals to warn ships of dangerous coastlines. Modern emergency sirens use repetitive tones that are specifically designed to capture attention and convey urgency even in noisy urban environments. The universal nature of repetitive warning signals suggests deep, evolutionary and physical principles that would apply to any intelligence that developed communication systems, regardless of its specific biological or technological characteristics. If our visitor is indeed artificial, if its patterns represent communication from non-terrestrial intelligence, then the repetitive nature of its signals might indicate that we're receiving some form of warning about conditions or events that require our attention. But what could an interstellar visitor be warning us about? The possibilities are both numerous and unsettling. The warning might concern astronomical threats that our current technology cannot detect, gamma-ray bursts from nearby stellar events, rogue planets approaching from interstellar space, or instabilities in our own sun that could threaten life on Earth. An advanced civilization with superior observational capabilities might be able to predict such threats far in advance, and could be attempting to warn us about dangers we haven't yet recognized. Alternatively, the warning might concern the consequences of our own technological development. Many scientists have speculated that technological civilizations face predictable challenges as they develop capabilities that could threaten their own survival. Nuclear weapons, genetic engineering, artificial intelligence, or space-based technologies that could trigger conflicts or environmental catastrophes. An intelligence that had successfully navigated these technological thresholds might be attempting to warn us about dangers that lie ahead in our own development path. The warning might even concern other forms of intelligence that we haven't yet detected. Perhaps our solar system lies along migration routes used by civilizations or artificial intelligences that could pose threats to developing worlds like Earth. The visitor might be alerting us to prepare for encounters with entities that operate according to principles we don't yet understand. But perhaps most disturbing of all is the possibility that the repetitive signals aren't warnings about future events, but rather about current conditions that we haven't recognized. The visitor's arrival coincides with a period of unprecedented change in human civilization, rapid technological development, environmental disruption, and social transformations that are proceeding at rates that exceed our ability to adapt or plan effectively. Perhaps the signals are attempting to alert us to the implications of our own behavior, patterns in our development that might be visible to external observers even when they remain invisible to us. The timing of the visitor's arrival and the repetitive nature of its signals suggest urgency that transcends mere scientific curiosity, something important enough to justify the enormous energy expenditure of interstellar travel, something significant enough to warrant continuous broadcasting of complex patterns, something urgent enough to demand immediate attention from any intelligence capable of recognizing artificial signals. Whether the warning concerns external threats, internal dangers, or conditions we haven't yet recognized, the repetitive nature of the visitor's communication suggests that time may be limited for whatever response is expected or required. As human observers around the world continued to monitor the visitor's patterns, searching for deeper meaning within its mathematical structures and geometric precision, they began to realize that they might not be engaging in pure scientific research. They might be receiving the most important warning in human history, broadcast across interstellar distances by intelligence that understood something about our situation that we had not yet recognized ourselves. The steady pulse of artificial patterns continued to emanate from our cosmic visitor, repeating with the mechanical persistence that evolution has taught us to recognize as signals too important to ignore. But the universe seemed to be offering us more than just the signal itself. It was providing context through the behavior of institutions and governments that were responding to the discovery in ways that suggested they understood far more about its significance than they were willing to reveal publicly. There are moments in the history of science when the most revealing information comes not from what institutions say, but from what they carefully avoid saying. When press releases focus on mundane details while ignoring extraordinary discoveries, when raw data flows freely through scientific channels while interpretive analysis disappears into bureaucratic silence, when the absence of official explanation becomes more significant than any explanation could be, our interstellar visitor was creating exactly such a moment. The timeline of institutional response to the discovery revealed a pattern that was both subtle and deeply troubling. March 2025. Automated analysis systems at the Catalina Sky Survey first detected mathematical patterns in the visitor's brightness data. Initial reports flagged the anomalies as potential instrumental artifacts requiring further investigation. April 2025. Independent confirmation arrived from observatories around the world. The European Southern Observatory's Very Large Telescope, the Panoramic Survey Telescope and Rapid Response System, and NASA's Deep Space Network all reported identical pattern detection in their measurements. The artificial nature of the signals became undeniable to anyone with access to the raw data. May 2025. Major space agencies began releasing carefully curated information about the visitor. NASA published detailed positional measurements, orbital calculations, and spectroscopic analysis. The European Space Agency released high-resolution images and trajectory data. The raw numbers were made freely available to the scientific community through standard astronomical databases, but something crucial was missing from these official releases. None of the institutional statements mentioned the mathematical patterns. None of the press releases discussed the geometric precision of the visitor's trajectory. None of the scientific papers submitted to peer-reviewed journals addressed the artificial characteristics that had become obvious to anyone analysing the complete dataset. The omission was so systematic, so consistent across multiple agencies and institutions, that it appeared coordinated rather than coincidental. June 2025 through the present. The pattern of selective disclosure continued with mechanical precision. Technical data flowed freely. Interpretive analysis remained absent. Official communications focused exclusively on the visitor's physical characteristics, while maintaining complete silence about its behavioural anomalies. This institutional behaviour followed historical precedents that were both instructive and unsettling. The scientific establishment has faced similar challenges when confronted with discoveries that challenged fundamental assumptions about reality. In each case, the response followed predictable patterns that revealed the conservative nature of institutional knowledge and the powerful forces that resist paradigm shifts in human understanding. Continental drift theory provides a classic example of institutional resistance to revolutionary ideas. When Alfred Wegener proposed in 1912 that continents moved across Earth's surface over geological time, he presented compelling evidence from multiple scientific disciplines, matching fossils across ocean basins, identical rock formations on different continents, and paleoclimatic data that made sense only if continents had previously been connected. The evidence was strong enough to convince many researchers that continental drift was real. But the geological establishment rejected the theory for over 50 years, not because the evidence was insufficient, but because it challenged existing models of Earth structure and dynamics. Scientific journals refused to publish papers supporting continental drift. Academic conferences marginalized researchers who advocated for the theory. Textbooks continued to present static continental positions as established fact despite mounting evidence to the contrary. The institutional resistance continued until the 1960s, when seafloor spreading and plate tectonics provided mechanisms that made continental drift not only plausible, but inevitable. Only then did the scientific establishment embrace ideas that had been supported by evidence for decades. Ball lightning presented a different but equally illuminating example of institutional denial. For centuries, people reported observing luminous spheres that appeared during thunderstorms, persisted for seconds or minutes, and then disappeared without trace. The reports came from reliable witnesses including scientists, pilots, and meteorologists, yet the scientific establishment consistently dismissed ball lightning as optical illusion, misidentified conventional lightning, or psychological phenomena. The dismissal persisted despite accumulating eyewitness accounts because ball lightning didn't fit existing models of atmospheric electricity. If it was real, it implied electrical phenomena that current physics couldn't explain. Rather than acknowledge the limitations of existing theory, institutions chose to deny the reality of the observations. Only when video documentation became common in the late 20th century did mainstream science grudgingly acknowledge that ball lightning was real, even though the physical mechanisms remained poorly understood. These historical examples revealed a consistent pattern in how institutions respond to anomalous discoveries. First, deny the reality of the observations by attributing them to instrumental error, misinterpretation, or observer bias. Second, if the observations prove undeniable, minimize their significance by focusing on conventional aspects, while ignoring anomalous characteristics. Third, delay interpretive analysis by demanding extraordinary levels of proof, while continuing to study the phenomena through conventional frameworks that preclude revolutionary conclusions. Our visitors' institutional treatment was following this pattern with textbook precision. The visitor's existence couldn't be denied. Too many independent observatories had detected and tracked it. But its anomalous characteristics could be ignored through selective reporting that emphasized conventional measurements while omitting discussion of artificial patterns. The strategy was effective precisely because it maintained plausible deniability while controlling public understanding of the discovery's significance. Raw data releases allowed institutions to claim transparency and scientific openness. Professional astronomers could access the measurements they needed to confirm the visitor's anomalous behavior. But the general public, lacking the technical expertise to interpret complex astronomical datasets, remained unaware that the data contained evidence of artificial intelligence. This approach served multiple institutional interests simultaneously. Space agencies avoided the political complications that would inevitably arise from officially confirming extraterrestrial intelligence. Scientific institutions protected their credibility by avoiding association with claims that might later prove false or misinterpreted. Government agencies maintained control over information that might have national security implications. But the strategy also created unintended consequences that were becoming increasingly difficult to manage. Independent researchers with access to the raw data began conducting their own analyses and reaching conclusions that contradicted official silence. Online forums dedicated to astronomical anomalies proliferated, sharing analysis techniques and discoveries that mainstream institutions refused to acknowledge. Social media algorithms amplified discussions of the visitors' artificial characteristics, creating public awareness that exceeded anything generated by official communications. The democratic nature of information in the digital age was undermining traditional institutional control over scientific interpretation. Amateur astronomers with sophisticated computer equipment could perform signal analysis that rivaled professional observatories. Retired scientists and graduate students could dedicate unlimited time to pattern recognition that busy institutional researchers couldn't prioritize. Citizen science networks could coordinate global observations that exceeded the capabilities of any single organization. This distributed research community was reaching consensus about the visitor's artificial nature despite official silence, creating a parallel scientific discourse that operated independently of institutional approval. The contrast between institutional behavior and independent research was becoming increasingly stark. While official sources maintained studied silence about the visitors' anomalous characteristics, independent researchers were publishing detailed analyses of the mathematical patterns, geometric relationships, and communication structures embedded within the visitors' signals. While space agencies focused on conventional astronomical measurements, citizen scientists were developing sophisticated protocols for decoding the artificial information content. The institutional silence was having exactly the opposite effect from what was intended. Rather than minimizing public interest in the visitors' anomalous behavior, the absence of official explanation was creating suspicion that institutions were deliberately withholding important information. The contrast between freely available data and missing interpretive analysis was generating exactly the kind of speculation and conspiracy theories that institutional silence was supposed to prevent. Public trust in institutional credibility was eroding as people recognized the obvious disconnect between what the data revealed and what official sources were willing to acknowledge. The situation was made more complicated by international dimensions of institutional response. Different countries and space agencies were responding to the discovery with varying levels of openness and secrecy. Some nations were more transparent about sharing observational data. Others were more restrictive about releasing analysis results. The uneven international response was creating additional suspicions about national security implications and hidden agreements about information sharing. International scientific collaboration, normally a source of strength in astronomical research, was becoming a source of tension as researchers in different countries operated under different institutional constraints and disclosure policies. The institutional silence was also affecting the research community in ways that extended beyond the immediate discovery. Young researchers were learning that certain types of analysis and interpretation were professionally dangerous, regardless of their scientific merit. Grant funding was becoming more difficult to obtain for projects that might lead to controversial conclusions. Academic careers were being shaped by unstated but clearly understood boundaries around acceptable research topics and interpretive frameworks. The chilling effect on scientific inquiry was extending far beyond the immediate question of the visitor's nature, creating a culture of self-censorship that threatened the foundational principles of open scientific investigation. As months passed without official acknowledgement of the visitor's artificial characteristics, the silence itself was becoming the most significant aspect of the discovery. The institutional response was revealing more about human civilization's readiness for contact with extraterrestrial intelligence than any analysis of the visitor's signals could provide. It was demonstrating the powerful forces that would resist, control, and potentially suppress information about such contact when it occurred. The absence of explanation was becoming an explanation in itself, evidence that our institutions were not prepared for the implications of what their own instruments were detecting, and that the truth about our cosmic visitors might be too challenging for the existing structures of human knowledge and authority to acknowledge. In the growing archives of astronomical data, patterns continued to accumulate that suggested intelligence reaching across interstellar space to announce its presence through the universal language of mathematics and geometry. But in the meeting rooms and press offices of the institutions charged with interpreting that data, a different kind of pattern was emerging, one that revealed the limits of human readiness for the cosmic community that was apparently trying to welcome us into its ancient conversation among the stars. In the vast symphony of the universe, most sounds are noise, random collisions of particles, the chaotic tumbling of debris through space, the background hiss of cosmic radiation that fills every corner of reality with meaningless static. But occasionally, very rarely, a single note emerges from this chaos with such clarity and purpose that it transforms everything we thought we understood about the nature of existence itself. Pattern is the universe's way of announcing intention. When energy organizes itself into structure, when randomness gives way to order, when chaos crystallizes into mathematical relationships that persist across time and space, something profound is happening. The laws of thermodynamics tell us that entropy always increases, that systems naturally move toward disorder and decay. For patterns to emerge and maintain themselves against this universal tendency toward chaos requires work, energy, intention. Pattern is expensive, pattern is rare, and pattern, in a universe dominated by randomness, is almost always artificial. This fundamental truth about information and energy has guided scientific discovery for centuries. When astronomers detect regular pulsations from distant objects, they know they're observing phenomena that require explanation beyond simple chance. When biologists find complex molecular structures that serve specific functions, they recognize the signatures of evolutionary processes that shape matter according to survival pressures. When physicists measure precise mathematical relationships in natural phenomena, they understand they're glimpsing the underlying order that governs reality itself. But our interstellar visitor has presented us with patterns that transcend these familiar categories of natural organization. The mathematical constants embedded in its brightness variations, the geometric precision of its trajectory through our solar system, the sophisticated encoding structures hidden within its temporal rhythms. These patterns require not just energy and intention, but intelligence capable of abstract thought, mathematical understanding, and technological implementation on scales that dwarf human capabilities. We are witnessing something that challenges our most fundamental assumptions about our place in the cosmic order. For centuries, the question of whether we are alone in the universe has haunted human consciousness. We've searched the skies for radio signals, examined meteorites for microscopic life, and launched spacecraft to explore the worlds of our own solar system. We've developed increasingly sophisticated instruments and analysis techniques, always hoping to detect some sign that intelligence exists beyond the boundaries of Earth. But perhaps we've been looking for the wrong kinds of signals. Our search strategies have been shaped by assumptions about how extraterrestrial intelligence might choose to communicate. We've expected obvious radio transmissions, dramatic displays of technology, or clear attempts at linguistic contact using mathematical or symbolic languages we could readily interpret. Instead, we may have discovered something far more sophisticated: communication through the manipulation of natural phenomena themselves. The visitor's approach represents a form of messaging that transcends the limitations of conventional signal transmission. Rather than broadcasting radio waves that might be missed, misinterpreted, or blocked by interstellar medium, it has embedded information within its own physical behavior, creating a mobile transmission platform that delivers its message directly to our cosmic neighborhood. This approach has several advantages that suggest deep understanding of the challenges inherent in interstellar communication. First, it ensures message delivery. Radio signals weaken with distance and can be absorbed or scattered by interstellar dust and plasma. But a physical object carries its information content intact, across any distance, immune to the interference that might degrade electromagnetic transmissions. Second, it provides context. The visitor's mathematical patterns and geometric relationships are embedded within phenomena we can observe and measure using our existing technology. We don't need to develop new instruments or detection methods. We simply need to apply our current capabilities more carefully and systematically. Third, it demonstrates restraint and wisdom about the psychological challenges of first contact. The discovery process has unfolded gradually, allowing us time to recognize the artificial nature of the patterns without triggering panic or premature responses. Each layer of analysis has revealed deeper complexity, but always within frameworks that our current mathematics and physics can comprehend. We're being led step by step toward recognition of intelligence, without being overwhelmed by capabilities so advanced they would render us helpless or terrified. This suggests intelligence that has thought carefully about the challenges of contact between civilizations with vastly different technological capabilities. But perhaps most significantly, the visitor's communication method demonstrates understanding of a principle that human psychology and information theory both confirm. We pay attention to patterns we discover for ourselves far more than to information that is simply transmitted to us. The patterns hidden within the visitor's data have required active participation from human researchers to detect and decode. We've had to develop new analysis techniques, apply sophisticated mathematical tools, and engage in collaborative efforts that have expanded our capabilities as a species. The discovery process itself has been educational, teaching us skills we'll need for more advanced forms of interstellar communication. This suggests that the visitor's mission may be more complex than simple message delivery. We may be witnessing the opening phase of a contact protocol designed to evaluate and develop our readiness for participation in a broader community of intelligence. The patterns we've detected might represent tests of our observational capabilities, our analytical skills, and our psychological preparedness for the reality of cosmic intelligence. The anthropic principle suggests that we observe the universe from our particular perspective, not by accident, but because we're the kind of observers capable of making such observations. Similarly, we may be detecting these specific patterns not by chance, but because we've reached the technological and intellectual threshold where such detection becomes possible. The timing of the visitor's arrival supports this interpretation. We're living through a period of unprecedented technological development. Our computational capabilities, digital signal processing techniques, and international communication networks have reached levels that make pattern detection and analysis possible on scales that would have been inconceivable just decades ago. We've developed artificial intelligence systems capable of recognizing complex patterns in vast datasets. We've created global networks that allow real-time collaboration between researchers separated by continents. We've launched space-based observatories that can measure astronomical phenomena with extraordinary precision. Perhaps most importantly, we've developed a scientific culture that values evidence over assumption, that seeks natural explanations for observed phenomena, and that remains open to discoveries that challenge existing paradigms. These capabilities and attitudes may represent the prerequisites for recognizing and responding appropriately to subtle forms of interstellar communication. The visitor's patterns may be calibrated precisely to become visible to minds like ours at exactly this stage of our development. Sophisticated enough to recognize artificial design, but not so advanced that we would miss the educational value of the discovery process itself. This interpretation transforms our understanding of what we're experiencing from passive observation to active participation in cosmic communication. We're not simply detecting signals from distant intelligence, we're demonstrating our readiness to join a community of minds that spans the galaxy. Each pattern we recognize, each mathematical relationship we decode, each geometric structure we understand represents progress toward the technological and intellectual maturity that such membership requires. But this interpretation also raises profound questions about the nature of intelligence in the universe. If our visitor represents one example of minds that have mastered interstellar travel and communication, then the cosmos may be far more densely populated with intelligence than we've ever imagined. The silence we've interpreted as emptiness may actually reflect the discretion of civilizations that communicate through methods too subtle for developing minds to recognize. We may be surrounded by conversations we're only beginning to overhear. The implications extend beyond astronomy into philosophy, religion, and our understanding of consciousness itself. If intelligence is common enough in the universe to develop sophisticated contact protocols, if minds regularly traverse the distances between stars, if communication networks span galactic scales, then consciousness may be not an accident of evolution, but one of the universe's fundamental characteristics. We may be discovering that mind and meaning are as basic to cosmic architecture as matter and energy. But perhaps the most profound implication concerns our responsibility as the recipients of such communication. Once we've recognized the artificial nature of the visitor's patterns, we cannot pretend we haven't seen them. Once we've decoded the mathematical relationships, we cannot claim ignorance of their significance. Once we've understood that intelligence is reaching across interstellar space to make contact, we cannot continue to behave as if we're alone in the universe. The patterns we've detected carry with them the weight of cosmic citizenship, and the responsibilities that such membership entails, we are being invited to participate in something larger than our individual civilization, something that transcends the boundaries of species, world, and solar system. But invitation implies choice, and choice requires understanding of both the opportunities and obligations that cosmic communication represents. As our visitor continues its impossible journey through our solar system, broadcasting its complex patterns of mathematical beauty and geometric precision, it carries with it more than just information. It carries the possibility of transformation, not just of our understanding of the universe, but of our understanding of ourselves and our place within the vast community of intelligence that fills the cosmic deep. The patterns were always there, hidden within the noise of astronomical data, waiting for minds sophisticated enough to recognize intention within apparent randomness. We've developed the technological capabilities to detect them, the mathematical tools to decode them, and perhaps most importantly, the intellectual courage to acknowledge their significance. The signal has been received, the message has been recognized, the invitation has been extended. What happens next depends on whether we're ready to accept that the universe has been trying to welcome us home all along, not to Earth, which was always our starting point, but to the broader cosmic community where intelligence shares the ancient secrets hidden in the light of distant stars. In the end, the patterns we've discovered may not be messages at all, but rather recognition signals, ways for minds separated by vast distances to identify each other across the cosmic dark. And in learning to recognize them, we may have announced ourselves as ready to join the conversation that has been flowing between worlds since consciousness first looked up at the night sky and wondered if anything was looking back. The visitor's signals continue to pulse with mechanical precision above our heads, carrying their cargo of mathematical beauty and geometric truth through the solar system we call home. Whether we respond to their invitation or remain passive observers of cosmic communication will determine not just our future as a species, but our identity as participants in the greatest conversation ever conducted, the exchange of meaning and purpose between minds that have learned to reach across the infinity of space and time to touch each other with the light of understanding itself.